Hello guys, welcome back to a new session. In today's session, I will be explaining the section 3 of chapter 6, which is about we'll be talking about constant ionization of weak acids, constant ionization of weak bases, buffer solution. We'll be talking about how to form a buffer solution. And then we'll be talking about hydrolysis, the cation and anion hydrolysis in this section. The first part of the section, guys, is about the constant ionization of weak acids and weak bases. If you remember, refer back to chapter 3, we talked about the titration. There we said we are not able to calculate the hydronium hydroxide pH, POH, and to form a titration between the two weak solutions, weak acids and weak bases. We said we are not able to calculate the values of pH, POH, hydronium hydroxide because they are partially ionizable compounds. But in this section, we'll be talking how to find the hydronium hydroxide pH, POH of those solutions through a constant value we call Ka and Kb. Let us talk about those two values, guys. First, the constant ionization of acids, when a weak acid here ionizes, it will form the hydronium and an ion left. If you can notice, most of the weak acids remain non-ionized, as non-ionized molecule, which is almost 98.7%. But 1.3% of the acid ionizes or form the ions of hydronium and acetate. Guys, in the above solution, in terms of existence, we have the weak acid, the hydronium, and an ion. So three species of particles are existing. The molecule of non-ionized acid, hydronium, and acetate as well. How to write the equilibrium constant expression for that reaction, guys? Of course, if you remember, we talked about the equilibrium constant. We said equilibrium constant equals the concentration of products over the reactants, but we just include gaseous and aqueous molecules, guys. So let us theoretically write the equilibrium constant for the above equation. What do we have in the product? Acetate and hydronium. And in the reactant, H2O and acetic acid. That's the equilibrium constant for the reaction. But guys, you know that the concentration of H2O is constant. So we will not include the H2O as being with the varied or variable species. These concentrations of the aqueous varied, but this is constant. So we will take this to the other side to be with the equilibrium constant, in the side of the equilibrium constant. Here we took the H2O with the equilibrium constant. Both are constants into the left, and then the remainder is what? Hydronium with the anion over the weak acid concentration. Guys, the hydronium with the anion over the concentration of the weak acid, in chemistry we call as the Ka, we represent by Ka as constant ionization of weak acids. Constant or acid ionization constants. Through the Ka value, we will be able to determine the degree of ionization of the weak acids. How? Because Ka can be obtained by dividing the hydronium and ion of the weak acids the acids to the concentration of the molecules of non-ionized acid. So through the Ka value, we'll be able to determine what's the degree of ionization and how many molarity or the concentration of each ion in the solution. So represents this by Ka. And Ka is equal to hydronium multiply the anion to the concentration of the weak acid, or can be represented as what? As usual, in the monoprotics, these two are equal. We can say hydronium square over concentration of the weak acid. This can be written as well. Hydronium square over the concentration of the weak acid, or acetate the anion square, Ka equals the anion square over the concentration of the weak acid. Can be represented in all these forms Ka. So what's the relation between equilibrium constant and Ka, guys? K multiply H2O is equal to Ka. This is the representation between the equilibrium constant and constant ionization of acids. Or we can say Ka is equal to Ka divided by concentration of H2O. Also, this can be represented in as the derivative of the main equation. So there will be questions like that. The equations that represent the relation between equilibrium constant and constant ionization of acids. This is the representation equation between equilibrium constant and constant ionization of the acids. As we have Ka value for the acids, for the weak bases, there should be a constant ionization for the bases. Instead of using Ka, we use Kb for the weak bases. The A represents the acids, the B represents the bases. An example here, guys, ammonia reacts with H2O to form ammonium and hydroxide. If we want to write the expression of constant equilibrium expression, it's equal to the concentration of product over the reactant. Here we have got ammonium and hydroxide over H2O and ammonia. As we said for the Ka, that the concentration of H2O is constant, so take the H2O to be in the same side of the equilibrium constant expression. And what's the remainder? Ammonium multiplied to the hydroxide over the concentration of ammonia, which is the weak base. This value we call as the Kb, which is the base ionization constant or constant ionization of bases. So Kb is equal to what? Cation multiply hydroxide over ammonia, or we can say over the weak bases. Kb can represent, these two are equal as hydroxide square over the concentration of weak bases, or we can say cation square over the concentration of weak bases. This can be represented to find the value of the Kb. And then, guys, what's the relation between K and Kb? K multiply the concentration, or we can say Kb equal to concentration of H2O multiply the K, which is the equilibrium constant, and then K equals Kb over concentration of H2O. These two, this is the main and this is the derivative, represents the relation between constant ionization of weak bases with the equilibrium constant expression, guys. We use Ka and Kb values to calculate the hydronium, hydroxide, pH, pOH, degree of ionization of the weak acids and weak bases. Let us provide some notes about the Ka and Kb, guys. Concentration of water is not included in the equilibrium expression. Why? Because water is liquid. We said the concentration of liquids and solids are constant. The term of Ka called the acid ionization constant. Ka value changed by changing temperature. This is important. How to change the Ka? By changing temperature. And Ka of strong acid is very large, so Ka of strong acid is much higher than Ka for weak acids. Why? Because Ka equals the hydronium with the anion over the concentration of the acid. For the strongest guys, mostly it completely ionized to form the ion. So the ions, the numerator is a higher value than the denominator. You get a high value. So the Ka higher than 1, that means the strong acids. If Ka lower than 1, then that means weak acids. Why lower than 1? Because the ions will be much lower than the concentration of the weak acid in the weak acid solutions. So representing the Ka value, a large Ka value represents a stronger acid, low K value represents a weaker acid. We can say higher than, the range higher than 1 Ka represents the strong acid, is lower than 1 represents what? The weak acids. With the Ka, we have Kb base ionization constant or constant ionization of bases. Value for weak base represents a small value. Why? Because as we said for Ka, the Kb of weak bases much lower than Kb for strong bases. Or we can say Kb for weak bases is much lower than 1, Kb for strong bases higher than 1. Why? Because in here completely dissociate the strong bases to form the ions. The concentration of ions are much higher than the non-dissociated bases. But here the concentration of the non-ionized weak acid molecule is much higher than the ions. Kb value for a strong base represents a very large value. We have to know that Kb for strong bases and weak bases, how it changes as we represent. Kb as Ka changes by changing temperature. So Kb, K equilibrium constant, guys. Ka, Kb, Kw value are those values that change only by changing temperature. Equilibrium constant, constant ionization of acids, constant ionization of bases, the constant ionization of water are changing by changes what? Changing the temperature of the medium, guys. In terms of providing the questions, guys, let me provide a question and then throw the values of concentrations, calculate the Ka, or maybe the Ka may be given and requires to calculate the concentration of one of the ions. For a solution, if concentration of HF equals 1.110 to the power minus 5 molarity. 1 to the power minus 5 molarity. If Ka for that solution equals 110 to the power minus to the Ka value, constant ionization of the acid. Calculate the hydronium, hydroxide, pH and pOH. When Ka is given with the concentration of the weak acid, how to calculate hydronium, hydroxide, pH and pOH, guys? We have to write the equation of Ka, guys. This is the solution. Ka is equal to hydronium concentration square, or we can say hydronium multiplied to the anion, but instead of writing an ion and hydronium both, we just write the hydronium square over the weak acid concentration. From the question, guys, from the question, Ka is given, which is 1/10 to the power minus 2. The concentration of the weak acid is given. So we will be able to calculate hydronium in this question. Let me solve for the hydronium in this part. Hydronium square equals the constant ionization of the weak acid multiplied the concentration of the weak acid, which is 1/10 to the power minus 2, 1/10 to the power minus 5. 1/10 to the power minus 2 multiply 1/10 to the power minus 5. This value will be something. 1/10 to the power minus 7. Okay? And this is equal to the hydronium square. Let me take the calculator in order to solve this, guys. Today I have a calculator, so I will be writing the square root of this value. How to write to the power of minus 7 open a bracket, the square of it is equal to 0.71. If it is, let me do again, guys. 1/10 to the power minus 7. No, it's not 0.71. It's equals 3.16 10 to the power minus 4 molarity. So this is the concentration of hydronium in the solution. Through the hydronium by using Kw, we will be able to calculate the hydronium hydroxide. We have this, and this is 1/10 to the power minus 14. So just divide this by this value, you'll get hydroxide. And by taking the negative log of this, let me take the negative log for this value, 3.16 10 to the power of minus 4. You'll get a pH of 3.5. The pH is 3.5, and then 14 minus 3.5, 10.5 pOH. These are the values of pOH, pH, hydronium and hydroxide can be calculated as well. That's how we can solve the questions related to the weak acids and weak bases. How do we able to calculate the hydronium concentration for a weak acid? Because the value of Ka is given. The value of Ka is given. This is a hypothetical question, guys. I have solved it. That represents the procedure will be shown as like that. The same for the weak bases. there should be the same procedure for the weak bases, guys. I will not do for the weak bases because it has the same procedure. There should be value of Ka or Kb given, concentration of the weak acid and the weak base is given, or the concentration, if it's not given, there should be some values, volume or moles, to calculate the concentrations, and then you'll be able to calculate hydronium for the weak acids directly and hydroxide for the strong weak bases. Okay guys, I will be showing you another relation between Kw and K. There should be some, we can take a relation like that. Guys, if you remember, Kw is equal to the concentration of hydronium multiplied to the concentration of hydroxide. And from the self-ionization of water, which is H2O plus H2O to form hydronium and hydroxide. Okay, in this case, guys, two water molecules self-ionize to form hydronium and hydroxide. Let us write the equilibrium constant for the above equation. Equilibrium constant for the above equation can be represented like that. Hydronium concentration multiplied the hydroxide concentration over H2O concentration squared. H2O concentration squared. Guys, in this part, instead of Kw, or instead of hydronium and hydroxide, we will write Kw, because here we have got hydronium and hydroxide multiplication, so it's equal to the Kw. K is equal to Kw over concentration of H2O squared, or Kw equals K multiply H2O concentration square. That's a representation of the equation which represents the relation between a constant ionization of water with the equilibrium constant. Let us talk about the buffer solution, guys. We'll be talking about the buffer solution, define what's a buffer solution, how to know whether a solution is buffered or not. The buffer solution refers to a solution that resists change in pH. So any solution resists change in pH we call as the buffer solution. So in buffer solution, it has a property, a tendency that does not let the pH of a solution changes while we add an amount of strong acids and strong bases. In order to understand the buffer solution, let us talk about figure 8, guys. In figure 8 part A, we have two solutions. The left solution is buffered solution, buffered. The right is not buffered or unbuffered solution. So when a solution is buffered with a solution which is not buffered, we will be talking about the difference between each of them when we add strong acids or strong bases to those. Both, guys, in this case, both they have a pH equals 5. Both they have a pH equals 5. The figure B, we added an amount of strong acid, which is here given the amount, 5 milliliter of 0.10 molarity. So an amount of strong acid, equal amount of strong acid to both solutions, the buffered and non-buffered solution. What we have observed, as you can see, there is no change in color of the buffered solution, but the solution of the non-buffered solution changes. Of course, we have added indicator for both solution in order to observe the color changes. Here the pH of a solution remain constant as 5, but the pH of this solution reduces to 2.17 as it's recorded here. That's the difference between a buffered solution with a non-buffered solution. A buffered solution, as you can see, by adding a small amount of strong acids or strong bases, resist change in pH, but the non-buffered solution has no such tendency to resist change in pH. What are the types of buffers? We'll be talking about the types of buffers and how to form buffers. The formation of buffer, we have two forms of buffer in our curriculum, guys. First, form a weak acid or weak base with its common ion when we add a strong acid and a strong base to those solutions. So we have got weak acid with its salt, add strong acid or strong base. Weak base with its salt, add strong acid and strong base to the solution. This is the first type of the buffer. A weak acid, a weak base with the common ion when we add a strong acid or a strong base to the solution. The second, guys, the second type is what? Is by a combination of strong acid with the weak base, strong base with the weak acid. This combination can form buffer, but with a specific condition, which the weak acid and weak base concentrations must be higher than strong acid and strong base concentration. This must be meted, should be meted in order to take the combination of these two as the buffer solution. The weak must be higher than the strong. The types of the buffer in terms of acidic and basic. What we mean by acidic buffer? We have got two types of acidic and two types of basic. Acidic buffer, we mean the weak side, the weak with the salt is weak acid. In this case, we have two parts. First, weak acid plus its salt, we add strong acid. Second, weak acid plus the salt, add strong base. We will be talking about each of them, the effect, what will happen, what's changed, what unchanged in these two cases. Guys, the first one is addition of small amount of acid, which is the strong acid. In this solution, I will be writing the equations CS3 plus CH3COOH plus H2O will produce CH3C negative plus hydronium. And with its salt, guys, if the weak is acid, the salt must be basic. If the weak is basic, the salt should be acidic. So let us add acid, but must have the acid contain the common ion with the salt must contain the common ion with the acid. For this, we have got CH3 COONA will produce CS3 COO negative plus Na positive. As you can see, these two are the common ions. Addition of a small acid means hydronium. So let us add a small amount of acid to the above equation, guys. or above solution. For example, HNO3 plus H2O will produce hydronium plus NO3 negative. Addition of a strong acid, as I told you, it's equal to the addition of the hydronium. Guys. As hydronium increase to the above equation, what will happen? What will happen to the concentration of hydronium here? It increases the concentration of hydronium somehow, but this is a buffer solution. The shifting equilibrium, the equilibrium direction shifts toward the left side, which is the reactant side, and we added hydronium in this direction, but in the other direction hydronium consumed. From this reaction we added hydronium to the solution, but hydronium, when increased by Le Chatelier's principle, increasing something in the product, shifts toward the reactant. What will happen in this case, guys? The hydronium hydroxide pH, POH stay unchanged. Hydronium hydroxide pH, POH, Ka does not change. Why? As I have represented, when the strong acid added hydronium, but in the weak acid reaction shifts to the reactant, and when it shifts to the reactant, that will consume hydronium, that will consume hydronium, CS3, C double negative, consume hydronium in this direction. So there will not be change in the hydronium total. In total, there will not be change. A small change there will be, but we ignore that, a small change. But what will happen to the concentration of H2O and CS3COOH, the amount, in terms of the amount, the non-ionized acid concentration increases. Why? Because the shifting direction goes towards the non-ionized acid, and water as well, water amount, molecules of water increases, there will be more formation of water. What will happen to the ionization of this acid? The ionization is in the forward direction, but in this case is reverse favorite, so the ionization of the acid decreases. Whenever we add a strong acid into an acidic buffer, the reverse direction will be favorite. There will not be change in pH, POH, hydronium, hydroxide, and Ka value as well, Kb as well, and then the concentration of non-ionized acid increases, but it is ionization decreases, guys. Let us, part B, add an amount of base. An amount of base to the acid buffer, acidic buffer. The same example, guys, let me write the same example. CH3, COOH, here is given, so I'll write the next example, the salt. CH3, COONA, dissociate to form CH3, C negative plus Na positive. This is the acidic buffer. And then what will be added? A base. Base, we mean a small amount of base is added, means hydroxide. The hydroxide of, for example, KOH, I dissociate to form K plus hydroxide. What will happen when we add hydroxide to the above solution? Guys, the amount of hydroxide, the added hydroxide, reacts with hydronium and reduce the hydronium at the beginning of the addition of the OH, reduce the amount of hydronium. And as somehow the hydronium reduced at the beginning, Let's the direction, the shifting to go to toward the formation of the product, because there will be some spaces here, we move it, so the direction, the shift in equilibrium shifts toward the product side to compensate the hydronium losage. In this direction, the concentration of the acid ionizes, so the ionization of the acid increases, but its concentration consumed, so the concentration decreases. In terms of hydronium hydroxide, pH, pOH, and Ka and Kb value does not change. Why? Because the removal of hydronium compensated by the ionization of the acetic acid, which there will not be totally, there will not be any change in the hydronium. As the hydronium unchanged, the other value of pH, pOH, hydroxide will stay constant as well. So whenever the acid added to acidic buffer, just know that acid added to acidic buffer, the reverse direction in the equation of the weak acid will be favored, its ionization reduced but concentration increase. There will not be change in value of pH, pOH, hydronium and hydroxide with the Ka and Kb. But as the base added to the acid will be the favorite direction shifts toward the product side, ionization of the weak acid increases, non-ionized acid concentration decreases. Let us answer this question, guys. When we add a base added into a weak acid and salt of a weak acid solution. Okay. Guys, a tip for ministerial exam, how to know whether the solution is buffer, how to know it talks about the buffer. Always in buffer there should be three components. Buffer with the common ion, somehow they are close to each other. But the only difference is that in common ion, the weak acid and the weak base are with the salt. They have a common ion in between. And then in common ion, we have the type for the strong acid and strong base with their salt. But here we do not have such type of buffer. And but the second type of the common ion, which is the weak acid, weak base with their salt, two components, we add the third component into them, that will be a buffer. As you can see, a base, which is the first component, added to what? Weak acid, the second component, its salt, the third component. How many components do we have? Three solutions, three components. So obviously this appears, the question is all about the buffer. A weak acid, HF, plus H2O produce hydronium plus F negative. Just write down in exam like that. KF produce K plus F negative. This is the common ion solution, and the buffer we add what? Base. Base means hydroxide. Addition of hydroxide reacts with the hydronium. As it reacts with the hydronium, the shifting goes toward the product side. Let us talk about what will happen. Weak acid molecule increases? No, its molecule decreases. Why? Because it must consume. Ionization of weak acid increases? Yes, this is true. Why? Because the weak acid ionizes more. A precipitate will form? No. Hydronium increases? No. In buffer solution there will not be change for the hydronium hydroxide pH and pOH. The second type of buffer, which is basic buffer, guys. In basic buffer we have a container which contains a weak base plus its salt, and we add acid, a strong acid, Or the second type, weak base plus its salt, we add a strong base into it. Let us talk about each of these two types, guys. The first, a small amount of base added to a basic buffer. Guys, ammonia reacts with H2O to form ammonium plus hydroxide. A salt that contains the ion of ammonium, for example, NH4Cl, dissociate to form ammonium plus Cl. This is the buffer solution. What we add into this solution? Hydroxide. Hydroxide means strong base. Hydroxide will increase the concentration of hydroxide initially, and then the hydroxide increases, shifts the reaction toward the reactant side. What will happen to the concentration of ammonia? Increases, but its ionization decreases. What will happen in total to the concentration of hydroxide? Stay unchanged. As hydroxide stay unchanged, hydronium, pH, pOH, Kb value stay unchanged as well. So the properties or for the basic buffer in this case, when we add a base, hydronium hydroxide, pH, pOH, Kb does not change, but non-ionized concentration molecules of the weak base increases, its ionization decreases. Let us add an amount of acid, a strong acid which represented by hydronium, into what? Into a basic buffer, which is the weak side is base. Here we have got ammonia reacts with H2O to form ammonium and hydroxide, and then the same example, NH4Cl will produce NH4 plus Cl negative. These two are the commons. Add the hydronium to the above equation. As hydronium added, that will react with the hydroxide, and hydroxide will be initially reduces, so let's the direction to shift toward the product side. As the direction shifts toward the product side, the concentration of the weak acid molecule decrease, but its ionization increase. The ionization of the weak acid molecule increase, but the concentration reduces because there will be consumption in the amount of the ammonia. But in terms of the hydroxide, in total, when we remove hydroxide initially, compensated by the ionization of the ammonia, in total there will not be change in hydronium, hydroxide, pH, pOH, Kb values does not change. Added acid donate proton to hydroxide ion to form non-ionized water. So as I told you, the hydroxide reacts with hydronium to form H2O. Some of the concentration of hydroxide decreases to release stress. Ammonia will ionize further to compensate the concentration of the hydroxide. In this direction, ammonia ionizes to produce hydroxide. Let us answer this question, guys. If NaOH is added to a solution, so NaOH is base added to a base. Guys, keep in mind, when both are the same, a base added to basic buffer, acid added to acidic buffer, the direction, the favorite direction goes to the reverse. But if they differ, the favorite direction goes toward the forward direction. So in this case, guys, NH3 plus H2O will produce NH4 positive plus hydroxide. If we add, of course, this should be with the base the salt, sorry. The salt is what, for example, NH4 Br will produce NH4 positive plus Br negative. And when we add hydroxide increase this hydroxide and then reverse favorite. That's why I told you whenever the added amount of the solution and the buffer solution are both the same, reverse favorite. If they are not the same, forward favorite. What will happen? Concentration of hydronium ion increased. It's not true because it's a buffer solution. How to know it's a buffer solution? One solution, two, and three solutions. So we have three components here. That's how we can recognize it's a buffer solution. Moreover, weak acid ionizes. It talks about the weak base. It's not about the weak acid. More hydroxide ions form. In the solution, no, the hydroxide will not be changed. More water and non-ionized base form. When we add hydroxide here, this consume hydroxide to form more water and ammonia. So D is the correct answer. Which mixture of the following solution is a buffer solution? So whenever asked about it, which of the following form a buffer solution, we have always to choose the salt with the weak acid and a weak base, which they have a common ion in between. Weak acid with the basic salt, strong weak base with the acidic salt, which they have common ion in between. NaCl and HCl, no, it's strong acid, cannot be taken. HNO2 with NaNO2, yes, because this is a weak acid with a basic salt. NaCl, HNO2, no, they don't have common ion in between, and this is a neutral salt. None of them, so B is the correct answer. Application of buffer, guys, just for information that our blood, the human blood, is buffered, and human blood is naturally buffered to maintain a pH of between 7.3 till 7.5. Why? Because change the pH of the blood may cause several sicknesses, and that large change in pH would lead to serious disturbance of normal body functions. That will disturb the body functions. That's why the pH must be must be buffered to resist change in pH. The solutions must be buffered to change the pH. There should be a resistance of the pH. Many consumer products are buffered to protect the body from potentially harmful pH changes. As you can see, this is written a buffered aspirin. Most of the medicines, they are buffered in order when we take those pills, those medicines to not change or affect the solution, the pH of blood. Here we have got ionization constant of water. If you remember, we talked about the self-ionization of water before, and we said when two water molecules are ionized, they will form hydronium and hydroxide. And how to write the Kw? Kw represents the constant ionization of water equals the multiplication of hydronium and hydroxide, and at 25 Celsius equals 1 10 to the power minus 14. Solid and liquid phases cannot written in the equilibrium equation, as we said this, and Kw changes by what? By changing temperature. We talked about this before in the self-ionization of water, guys. Let us talk about the hydrolysis of salts. We'll be talking about the types of salts and what's hydrolysis, how hydrolysis will be processed in this part. Guys, salts in general, we defined the salts in the previous sessions. We have got four types of salts. a salt of a strong acid and a weak base. If any of this is strong, base or acid is strong, the salt will be takes the name of the strong. So here in this case, the strong acid and a weak base is acidic. Why? Because the strong is acid. The second one, a salt of a strong base and weak acid, so the base is strong, is basic. A salt of a strong acid and a strong base, both are strongest, will be neutral. And a salt, additionally, from weak acid plus weak base can be all of the above, depends on the Ka and Kb we will be talking about in detail. Guys, these salts, the ions formed are from weak acids or bases. They react with the water molecule and the pH of a solution will have another value than 7. In some of these salts, when they dissociate, they will form an ion. That ion has tendency to react with water and change the pH, POH, hydronium hydroxide of the medium. This reaction between water molecule and ions of dissolved salt, a reaction between water and ions of a dissolved salt, we call as hydrolysis. So simply hydrolysis is what? Is a reaction of an ion from a dissolved salt with water. But all of the ions? No. We'll be talking about what ions undergo through hydrolysis, what are not undergoing through the hydrolysis. Let us talk about the types of hydrolysis. We have got two types of hydrolysis. As we talked about the types of buffer, let us talk about the types of hydrolysis. Guys, hydrolysis can be formed from ions of weak acids and weak bases, ions or from the weak acids and weak bases plus H2O. And as you know that an ion from a weak acid is a strong conjugate base. We are talking about an ion. From the weak base, cation is a strong conjugate acid. So here, the reaction of ions of weak acid and weak base with H2O is hydrolysis. Whenever the ion of the weak acid, which is an ion, let me provide an example. HF will provide hydronium and F negative. This F has tendency to react with H2O to form the F negative, to form HF and release hydroxide. So an ion from a weak acid is a strong conjugate base. For the second, NH3 plus H2O will produce NH4 plus hydroxide. This ammonium reactase is what is strong conjugate acid in this reaction. Reacts with H2O to produce ammonia plus hydronium. Plus hydronium. So here the hydronium increases, there the hydroxide. We'll be talking about them in detail. As you can see, from the weak bases, we get a strong conjugate acid. From a weak acid, we get a strong conjugate base. A strong conjugate base and a strong conjugate acid plus H2O reacts with H2O, this is the hydrolysis. And if it is strong conjugate base, an ion, the type of hydrolysis will be an ion because it refers the anion reacts with H2O. If it's from the weak base, which is a strong conjugate acid, reacts the ion which reacts with H2O is cation. That's why we call it cation hydrolysis. We'll be talking what's a cation and an ion. Simply, that's the was a simple explanation. Let us talk in detail. If the anions strong conjugate bases, so a strong conjugate base obtained from what? Weak acids. We obtain a strong conjugate base from what? From weak acids. Reacts with water, the process is anion hydrolysis and results in a more basic solution and will produce a basic salt. Will produce what? A basic salt. Let me represent the general equation for anion hydrolysis, guys. A negative is a what? Is a strong conjugate base from a weak acid, like what? For example, HF that formed F negative. This is a strong conjugate base. Okay. This has tendency, because it comes from a weak acid, it has tendency to react with water. When it reacts with water, will produce what? We'll take a proton from water, will produce the acid, and then increase hydroxide. So in general, anion hydrolysis. Why anion hydrolysis? Because the anion reacts with H2O. The anion comes from a weak acid, which is a strong conjugate base, reacts with H2O, increases what? Hydroxide. So what will happen to the hydroxide concentration? Increase. And pH as well increase. Hydronium and pOH decrease. So that's how we can understand the anion hydrolysis, what will happen. The solution becomes more basic. As you can see, the hydroxide, more hydroxide increases, the solution becomes more basic, and non-ionized acid molecule as well increases. It will produce the acid molecule more, HA. This is the non-ionized acid molecule, will be formed more. Let us talk in detail about this example. Here we have got a strong conjugate base. Strong conjugate base. So a strong conjugate base comes from what? Obtained from the weak acid. That's why it has tendency to hydrolyze with water to produce hydroxide and weak acid as well. Here increasing the hydroxide increases pH, decreases hydronium and pOH. The concentration of the non-ionized acid as well increases. So you have to know that what's going on in the anion hydrolysis and the general equation for the anion hydrolysis as well. Amount of hydroxide ion formation depends on the relative strength of the anion. If the anion is more stronger, comes from the weak acids, it will produce more hydroxide. The lower the Ka, the stronger the attraction of F negative. The lower Ka means a weaker acid. So a weaker acid produces a stronger conjugate base, and the proton will have 4 protons. This has more attraction for protons, and the larger concentration of hydroxide will be formed in total. In other words, the weaker the acid, HF, the stronger its conjugate base. We talked about this in strength of conjugates previously. As the acid becomes more weaker, it will produce more stronger conjugate bases. As it becomes more stronger, that will hydrolyze more with water to produce what? Attract protons more from water to produce hydroxide and increase the alkalinity of the medium. So the properties of anion hydrolysis we'll be talking about later. Let us talk about cation hydrolysis as well, and then we'll be talking about in summary about those hydrolysis. A cation hydrolysis, the cation which is a strong conjugate acid from a weak base reacts with H2O. So in this case, strong conjugate acid from what? From a weak base, from a weak base, reacts with H2O to increase hydronium. The procedure calls what? Cation hydrolysis. Because strong conjugate acids are cations from the weak bases and will produce acidic salt, and the solution becomes the more acidic. The solution becomes more acidic, hydroxide and pH decrease, hydronium pH increase, non-ionized base molecule increase. What's the general representation for the equation of cation hydrolysis? BH positive represents the cation hydrolysis like NH4 positive, guys. Here we have got an example. When it reacts with water, it's what? It acts as a strong conjugate acid because it comes from a weak base. Reacts strongly with the H2O to produce hydronium and the base as well. This increases the hydronium concentration and increases the weak base concentration. As hydronium increase, what will happen to the hydroxide? Reduce. Hydronium increase, what will happen to pH? Reduce, and pH increase. Example, let us take this as an example, guys. NH3 produces ammonium, which is strong conjugate acid. This strong conjugate acid comes from a weak base, so it reacts with water to produce hydronium, and concentration of the ammonia as well increases. So in this case, the hydronium increases, hydroxide decreases, pH decreases, pOH increases, concentration of the weak base increases as well. And amount of hydronium formation depends on what? On the strength of the ammonium. As the base becomes more weaker, will produce a stronger conjugate base acid, and as the conjugate acid becomes more stronger, it donates proton, greater tendency to produce hydronium concentration because it donates proton more, and then the lower the Kb value, we can say, the weaker the base but the stronger its conjugate acid. As the Kb value reduces, the base becomes more weaker and its conjugate becomes more stronger. So the properties, in summary, the properties of anion hydrolysis and cation hydrolysis. Anion hydrolysis, the hydroxide and pH increase, guys, but hydronium and pOH decrease. There will not be change in Ka and Kb values. Amount of non-ionized acid molecule increases. But for cation hydrolysis, it's just the opposite. Hydroxide and pH decrease, hydronium and pOH increase, Kb and Ka value does not change. Amount of non-ionized weak base molecule increases. This is a summary for both procedure, but in general the structure is very important. A negative plus H2O. A negative is a strong conjugate base, will produce the HA and hydroxide. This one as well, BH positive plus H2O will produce B plus hydronium. This is very important to be known. The concentration of the weak acid increase, here the weak base increase, the hydroxide increase, here hydronium increase. That will be the summary of the cation and anion hydrolysis. Let us talk about these notes, guys. Strong conjugate base of weak acid hydrolyzed with water. Strong conjugate base. Strong conjugate base we can obtain from what, guys? From weak acids. Example, There will be questions, a type of question that will ask, which of the following ions hydrolyze? Which of the following ions hydrolyze? If asks about which of the following ions hydrolyze, you have to choose an ion that's a strong conjugate acid or a strong conjugate base, but obtained from weak acid and weak bases only. So PO4 negative obtained from what? From S3PO4. S3PO4 is weak acid, can hydrolyze, anion hydrolyze. SO3 negative 2 obtained from H2SO3, anion hydrolyze again. Coming from HNO2, HNO2 is a weak acid. These are all weak acids, and these are all strong conjugate bases. They can undergo through anion hydrolysis. Negative ion coming from weak acid hydrolyzed with H2O. Another example, SO4 negative 2 with H2O. If it comes, these are all strong acids, and this becomes weak conjugate bases, guys. These ions. A weak conjugate base from strong acids cannot undergo through hydrolysis. Cannot undergo through hydrolysis. So, if negative ion coming from a strong acid, the ion is weak conjugate base, so it cannot undergo through hydrolysis. They cannot hydrolyze with water. A group of anions which are strong conjugate bases can undergo through hydrolysis, which they come from weak acids, but a group of anions which are weak conjugate bases obtained from strong acids, they cannot undergo through hydrolysis. Second, about the bases, guys. Strong conjugate acids which obtained from weak bases undergo through hydrolysis, like NH4 positive coming from ammonia, C6H5NH3 coming from C6H5NH2 aniline. These two they are the strong conjugate acids from weak bases, can undergo through cation hydrolysis. But guys, we have some more notes here. Metal hydroxide cannot hydrolyze H2O, such as NaOH, KOH, because do not have conjugate acid, so cannot hydrolyze. Keep in mind, the metal hydroxides, they cannot hydrolyze with water because they are not having conjugates. And then next, neutral salts do not undergo through hydrolysis, such as KBr. In terms of the salts, guys, the neutral salt does not hydrolyze. Does not hydrolyze. Neither anion nor cation. Acidic salt, like NH4Cl, here like KCl. Acidic salt, guys, only cation hydrolyze. Basic salt, like the KF, only anion hydrolyze. Anion hydrolyze. The fourth type of the salt, which NH4CN, both from mix, both hydrolyzes. Both hydrolyzes. Both hydrolyze means what? Means cation and anion. Cation and anion hydrolysis. Let us answer the following questions, guys. Which of the following ions hydrolyze? You have to choose an ion of a strong conjugate acid, strong conjugate base from weak acids and weak bases. This is not, because it obtains from HNO3, a strong. This is yes, because obtained from a weak acid. This KOH cannot undergo through hydrolysis. This H2SO4 cannot undergo through hydrolysis. So whenever asks about the ions, choose the ions that obtain from weak acids and weak bases only. Which of the following contain only cation hydrolysis? May specify the type of the hydrolysis as well. So you have to choose for the cation hydrolysis, guys. Cation hydrolysis, choose if the salt is given, choose the acidic salt. Acidic salt. If anion hydrolysis is required, choose the basic salt. Here, which one? KCl is neutral, NaCN is basic, NH4CN both hydrolyzed, NH4Br is, guys, this does not undergo through hydrolysis. This is anion hydrolysis. Why? Because the CN is a strong conjugate base from a weak acid. This both hydrolysis, C. But D is what is cation hydrolysis. So whenever requires cation hydrolysis, choose an acidic salt. Whenever it requires anion hydrolysis, choose a basic salt. When it requires both hydrolysis, choose a salt from two weak acids and weak bases, guys. More questions? According to hydrolysis, which one is odd? Which one is odd? NO3 negative does not undergo through hydrolysis. F undergo through hydrolysis. K does not undergo through hydrolysis. SO4 negative does not undergo through hydrolysis. So it means B is odd. Why B? The only one ion which undergoes through hydrolysis is B. Which one of the following salt does not hydrolyze? A salt that does not hydrolyze is a neutral salt. So simply choose a neutral salt, which is Na2SO4. This undergoes through cation hydrolysis, NH4Cl. This one, anion hydrolysis, NaF, and KCH3COO, anion hydrolysis as well. Which of the following ions hydrolyze in aqueous solution? Which of the following? The same ions from the weak acids and weak bases. This undergoes through hydrolysis, not. Which of the following does not hydrolyze? When it requires does not hydrolyze, just use the technique that we said. NaOH does not hydrolyze. CH3COOH, it undergoes through anion hydrolysis, has an ion that undergoes through anion hydrolysis. NH4NO3 undergoes through cation hydrolysis. NaCN undergoes through anion hydrolysis. That's why the only one that does not hydrolyze is what is A, which is a metal hydroxide. We talked about this. Which of the following hydrolyze both anion and cation? In this case, choose a salt that from a weak acid, combination of a weak acid and a weak base. Guys, NH4CN, yes, no. So A is the correct answer. Why? Because NH4 obtained from ammonia, CN from HCN. Which of the following only anion hydrolysis? Anion hydrolysis, you have to choose an anion if the ion is given from a weak acid, or if a salt is given, choose what? The basic salt. So here the first one is both hydrolysis. The second one is a basic salt, anion hydrolysis, so B is correct answer. The C is a neutral, does not hydrolyze. The D, both hydrolyze because it both comes from the weak acids and weak bases. So guys, here we have got some more explanations for the types of the buffer we said before. We said and the hydrolysis more explained here in general, the anion and cation hydrolysis as well. The cation hydrolysis represents more. We talked about the cation hydrolysis. Its equation is important. the types of the questions are as well is important, and let us talk about the hydrolysis in acid-base reactions, guys. Graphically, we will be showing what's the buffer region, how hydrolysis can help explain why the endpoint of a neutralization reaction can occur at the pH other than 7. So we will be using hydrolysis to talk about the titration procedures and to understand why we may have endpoint in different values, in the other values rather than 7. We have got strong acid and strong base. The salt is strong acid and strong base will produce what? Neutral salt, guys. Strong acid and weak base will produce what? Acidic salt. Weak acid and strong base, basic salt, guys. Weak acid, weak base, all can be all neutral, basic, and acidic. It depends on what? On the Ka and Kb value. If Ka and Kb values are equal, it becomes neutral. If Kb is higher than Ka, basic. If Ka higher than Kb, it becomes acidic, guys. Let me provide examples as well in order to know. Neutral, like Li2SO4, this is neutral. Acidic, NH4Br, basic, KF, both NH4F. These are the types of the salts which we have. Guys, the name refers to what? To the strong part, but the hydrolysis refers to the weak part. What do we mean by this? The strong acid and strong base produce neutral and does not hydrolyze. But strong acid and weak base, which one is strong? The acid. So it will take the name of the stronger one, which is acidic. But which one is weak? The weak base. So it will be what? The cation hydrolysis. The type of the hydrolysis from the weak, but the name of the salt from the strong. Weak acid and strong base, the base is stronger, so it becomes what? Basic salt. But the type of hydrolysis depends on the weak, which is anion hydrolysis, and the last one can undergo through both hydrolysis. Let us talk about the first titration between strong acid and strong base, which produce a neutral salt, guys. Salts of a strong acid and strong base produce neutral solutions because neither the cation of a strong base nor the anion of the strong acid undergo through hydrolysis. They will not undergo through hydrolysis. These two, neither potassium, cation of the strong base, nor the Cl undergo through hydrolysis. They do not hydrolyze. Therefore, aqueous solution of NaCl is neutral. Aqueous solution is neutral, and the graph can be represented as usual. We have represents the equivalence is at 7 pH of 7. And you have to know that a neutralization between strong acid and strong base will produce a neutral salt, and the pH is 7. Let us talk about the second titration between the acids and bases, which is strong base and weak acid. The aqueous solution of salts from reactions between weak acids and weak strong bases are basic equivalence greater than 7. You know that whenever the equivalence between strong base, weak acid, the reaction becomes, the equivalence becomes in a point in a region higher than 7, which is here represents the equivalence almost 9 above 7, and we have got four numbers. Let us talk in each point. What do we have? What decides the pH of the solution and the color of the solution as well. Guys, at point one, the prior to the addition of the base into the flask, we have only the acetic acid. So at point one, the titration curve, only acetic acid present. The acid present in point one. The pH depends on what? On the weak acid alone. We talked about that. The starting point of the graph depends on the pH of the solution in the flask. Second point, guys, as we add an amount of base, let me show you. Here we have got CS3, COOH, and then we will add an amount of NaOH. As we add NaOH, there will be what? Hydroxide. So it will produce what? Hydroxide. At point 2, there is a mixture of what? The acid and the anion of the acid, which we call as the buffer region. A buffer is what? Is a solution which we have the amount of the weak acid of weak base with the common ion of those weaks. That will be a buffer region. So in this region, in this point, the graph represents what? A buffer region. You can notice, guys, during the buffer region, the pH increases slowly. So this region resists change in pH. Resists change in pH. That's why it's not vertically jump. We cannot observe a vertical jump in pH because this region is a buffer region and the concentration of the acetate with the acetic acid, they both exist in that region. And adding NaOH change the pH slowly at point 2. Why? Because it's a buffer solution. But at point 3, all acids has been converted to acetate. Here, the acid ionized in this point or at this point, all of the CH3 COOH converted to form acetate and hydronium as well. So this hydrolyzes to produce a slightly basic solution. As you can see, guys, we have a weak acid and this is a strong conjugate base. We talked about hydrolysis. A strong conjugate base has tendency to what? To react with H2O and produce CS3 COOH plus what? Plus hydroxide. That's why above this region will be more hydroxide will be formed due to of what? Of anion hydrolysis. Anion hydrolysis. At point 4, the pH is due to the excess of hydroxide that has been added. At this point we can indicate the pH through what? Through the hydroxide that added to the medium through the addition of sodium hydroxide and through the hydrolysis of the acetate ion as well. So guys, weak acid with a strong base will produce a basic salt. A basic salt, why we call it basic? Because it undergoes through anion hydrolysis and the anion of the dissolved salt at hydrolyzed by the water molecule and the pH of a solution is raised, indicating that the hydroxide ion concentration has increased due to of the anion hydrolysis. Aqueous solution of sodium acetate are basic. The acetate ions undergo hydrolysis because they are the anion of the weak acid, which is the acetic acid. The third type of hydrolysis, guys, or the third type of titration and another form of hydrolysis is a titration between strong acid and weak base. Strong acid and weak base. We have got 4 pointers, point 1, 2, 3, 4. Okay? At point 1, in the flask, we have got only what? Ammonia. And then we'll add, for example, HCl to it. Okay? Point 1, the titration curve only, in the titration curve, only the aqueous ammonia is present, so the pH determined by the base alone. At this point, we have only base, the weak base. But after addition of HCl to the solution, the weak base starts to ionize. As it ionizes, there will be formation of ammonium, and in that region, the ammonium will be formed. Like this is the example, NH3 plus H2O will produce NH4 positive plus hydroxide. NH4 positive plus hydroxide. At point 2, there is a mixture of ammonia and ammonium, a buffer region. Adding HCl changes the pH slowly. Guys, in this case, we added HCl to the region, to the flask. HCl added will produce Cl and the hydronium, but ammonia ionized to form ammonium and hydroxide as well. So in this region, when we have a weak base with the common ion of that weak base, which is ammonium, we can say it's a buffer region, and as you can see, the change in pH is slowly, it resists change in pH. But at point 3, guys, all of the ammonia converted to ammonium. All of the aqueous ammonia has been converted to ammonium. And at this point, ammonium, which is a strong conjugate acid, reacts with H2O to form ammonia and hydronium as well. So it increased the hydronium concentration due to of cation hydrolysis. And at point 4, the pH is determined by the excess of hydronium that's been added to the medium. We can understand the buffer regions and the hydrolysis in the pointers. In the above, there were anion hydrolysis, here the cation hydrolysis, and the cation hydrolysis will produce an acidic salt. The cation of the salt undergo through hydrolysis because they are the positive ion from a weak base. A positive ion from a weak base is a strong conjugate acid. The anions of the salt are the negative ions from a strong acid and do not undergo through hydrolysis because it's a weak conjugate base. Ammonium chloride is a salt that produces an acidic solution because of cation hydrolysis. The fourth type of the salt, which is a weak acid and weak base. Salts of weak acid and weak base, guys, can be produced as to be acidic, neutral, or basic. It depends on what? It's because they both hydrolysis. Both ions, they have tendency to hydrolyze. And an example can be stated as NH4, CS3, COO, can be acidic, basic, or neutral. We will be talking when can be acidic, basic, and neutral in this notes. If salt formed from a weak acid and a weak base, the cation and an ion both undergo through hydrolysis. So NH4F, both anion and a cation, hydrolysis. If weak acid and weak base, we have Ka and Kb values. By determining the Ka and Kb values, we'll be able to know the type of the salt here. If Ka is higher, so it will be acidic. If Kb is higher, it will be basic. For weak acids and weak bases, salt depend on Ka and Kb value. In this case, when we have Ka and Kb, they are equal, it will produce neutral. Ka higher than Kb, it produces the basic, or we can say acidic. The Ka lower than Kb, it produces an acidic salt or basic salt. Here the acidic, here basic, here neutral salt. Neutral when Ka and Kb are equal. Acidic when Ka higher than Kb. Basic when Ka lower than Kb. That will be the but in all of these cases, it undergo both ions hydrolyze. It does not affect on the hydrolysis, to say only cation or anion hydrolysis, guys. Here we have got some combinations of the weak acid with the strong base and weak base with the strong acids, guys, to form a buffer or not. As you can see, the amount of the weak higher than the strong, at the result, there will be all the consumptions of the base. The strong base will be consumed. All of the strong base will be consumed. 0 mole left. But an amount of the weak acid remain with an amount of the salt. And as you know, whenever we have a weak acid with its salt, they will form a buffer solution. This is the type that I told you, the second type of buffer solution. But guys, if the amounts are equal, there will not be, the weak acid will not remain. In this case, there is no buffer solution. The solution will not be buffered, and just the salt remain. The salt is basic and it then go through anion hydrolysis. Another combination which the amount of the weak is lower than the strong. The weak has no existence, the strong has existence, so it will be it will not be a buffer solution. The solution cannot be classified as buffer. A buffer is formed when acid and bases are mixed together, but the weak must be higher than the strong. Concentration of the weak can be higher, must be higher than the strong. To understand, let us solve this question, guys. Which of the following mixture is a buffer solution? 0.2 NaOH and HF, this cannot be because the strong is higher. This cannot be because they are equal. This can be because the weaker is higher than the strong. This cannot be because the stronger amount is higher than the weaker amount. So whenever asks about the formation of this buffer solution, when the acids and bases the reacts, the weak must be higher than the strong. That will form a buffer solution. Here we have got the standardized test, ministerial questions. We'll be solving the standardized test prep at the end of the chapter, guys. Let us solve some ministerial exam question. If NaOH added to a solution, here we have 3 components, so it means a buffer solution and a buffer cases. A base added to base, the reverse favorite, as reverse favorite concentration of hydronium does not change. More of the weak acid ionizes, no. More of the hydroxide ion form, no. More water and non-ionized base form, D is the correct answer. Which of the following anion hydrolyzed, guys? Anion hydrolyzed, B is the correct answer. Why? Because ion from the weak base which undergoes through anion hydrolysis. When we add base into a weak acid and a salt, so three components of weak acid solution, which of the following is true? Base into acid, therefore what favorite? So weak acid molecules increases? No, it consumes more. Ionization of the weak acid increases? Yes. Precipitation? No. Hydronium, there will not be change in hydronium, guys. Aqueous solution of one of them is basic. Which of them has a basic aqueous solution? NH4Br, NaCN. Why? Because it's basic salt, and basic salt undergoes through anion hydrolysis and produce hydroxide. Which of the following is not true for anion and cation hydrolysis? The anion A acquires a proton from the water plus H2O will produce HA and hydroxide. Acquires proton from water? Yes, but it says what? Is not true. So this is true. In anion hydrolysis, form the weak acid. The weak acid will be formed. It's true. The cation hydrolysis, which is BH positive plus H2O, will produce B plus hydronium. BH positive, donate the proton to water. Yes, of course, donate the proton to water. It's not true. In cation hydrolysis, form the hydronium ion and the weak acid. It forms hydronium, but it will not form weak acid. It will form weak base. So this is the not true for and is a correct answer. It will produce weak base, not weak acid. Which of the following is not true for buffer solution? It can resist change in pH. Yes, it can resist change in pH. This solution KF and NaF is a buffered solution. KF and NaF, they are two salts. From two salts, we cannot form a buffer solution. So it said it's not true. This is not true. A solution in which either a weak acid mixed with its salt, yes, it can be formed a buffer. A solution in which weak base mixes with its salt is buffer, so B is the correct answer. Contain only cation hydrolysis. Cation hydrolysis for the salts, guys, I told you, you have to choose acidic salt. Which one is acidic salt? Acidic salt. D is the correct answer. Which mixture of the following solution is a buffered solution? Here choose the weak acid, weak base with their salts only. B is the correct answer. HNO2 plus NaNO2. The anion of a salt of a weak acid and a strong base is the anion of a salt of a weak acid and a strong base. Strong base KOH, weak acid KF. Anion of this is what is a strong conjugate base of conjugate acid, no. Hydronium ion, no. Conjugate base of a weak acid, yes, is a conjugate base of a weak acid. Which of the following solution is a buffer solution? You have to choose the weak acid with its salt. HCl, NaCl, no. HF, NaF, yes. B is the correct answer. It's the weak acid with its salt. Which of the following solution prevent change in pH means it's a buffer solution? Buffer. In which of the following salts only cation hydrolysis in aqueous solution? The salt should be acidic. So which one is acidic? This is both hydrolysis. This is anion. That's neither. D is the correct answer, which is cation hydrolysis. For a salt with a pH less than 7, which of the following ions undergo hydrolysis? Less than 7 means acidic salt, guys. Acidic salt, pH less than 7. Acidic salt undergoes through the cation hydrolysis, as you know. Which of the following cation contains the lowest hydronium ion concentration? Lowest hydronium ion concentration. This is weak acid, This is the acidic salt, H2O neutral. This is strong acid. H2O is the correct answer. Why? Because H2O contains the least hydronium concentration among those options. Guys, the last question, an amount of NaOH was added to a solution containing weak acid and is salt. This is buffer. Base added to the weak acid, they are different, so the forward will be favored. Increased concentration of the acid, no, it consumes the acid. Ionization of the acid, yes. Increased concentration of hydrogen, no. Precipitation, no. So B is the correct answer. Thank you for the attention. That's the end of the session.